The purpose of this experiment is to observe the application of the loop rule and the change in the potential of the parts of a circuit by using the circuit simulator and varying setups of resistors and capacitors. The simulated models used in this experiment were a battery, resistors, and light bulbs of varying resistance, and a capacitor that were all connected in an ideal circuit. The physical principles used in the experiment involve the changes in electric potential of the components of a circuit at steady and non-steady states. The overall result of this lab was that the simulated circuit reflected most of the physical principles and laws, and the calculated value of the time constant RC using the circuit reflected the actual resistance and capacitance in the time constant. Before observing the experiment, here are the fundamental principles and equations. The loop rule, which states that the sum of the potential differences of the components in a circuit is 0, was used to calculate the current of the circuit setup. To do this, the formula for the delta V of the capacitor and the Ohm's law for the resistor, as well as the node rule, was used. These formulas and the loop rule was used to derive this formula to find the time constant RC, obtained from the slope of the graph between time and the first term as shown here, the natural log of delta V over delta V naught. The reason for why the simulated circuit was used was in order to observe the physical principles of a circuit in an ideal setting, as having non-ideal conditions would produce unpredicted calculations for the resistance and the current of the circuit. Thus, the assumptions that there would be no leakage in the charge of the capacitor and the resistance of the wire and ammeter would be negligible were held. The system of this experiment contains the components of the circuit, including the wire, battery, capacitor, and the resistors. The surroundings is everything else. The initial and final condition of the simple circuit were the same over an extended period of time, and the final condition of the RC circuit had a current of 0, unlike the initial condition that had a non-zero current. Using the loop rule, the predicted current of the circuit setup in this first image was calculated to be 0.01 amps, and this was reflected in the ammeter in the simulated circuit. Using the voltmeter, the potential differences of each part of the circuit was measured below, and their sum equaled 0, which further proved the behavior of the loop rule. The potentials of these components were modeled in the graph of the potential and positions, which shows that the potential decreases through the resistors and eventually equals the initial delta V. The effect of the voltmeter on the current was shown to be 0, as the current was unchanged when the voltmeter became a part of the circuit, mostly due to its impedance. However, when the ammeter was placed parallel to one of the resistors, as shown in this bottom image, there was an increase in the current to 0.03 amps due to the node rule and the split in the current. Using this new current, the new resistance values were calculated using the Ohm's law. The behavior of an RC circuit was also modeled, which the process of charging the capacitor was shown to decrease the current over time, shown through the dimming of the light bulb. The capacitor was then discharged by connecting it directly to the light bulb, which the model showed the charge on the plate to decrease over time. The time it took for the capacitors to charge while connected to the light bulbs with different resistance was recorded below, and these time values were taken until the current in the circuit was 0. The formula used to calculate the RC constant was used and graphed by obtaining the initial change in potential and the change in potential over a 20-second frame and graphing their relationship between time. The slope of this relationship was obtained to be negative 0.166, and using the formula of negative 1 over RC, the time constant was calculated to be 6.024. In this simulated circuit, the predicted current using the loop rule, given the circuit layout, matched the current measured in the ammeter, proving the loop rule. Regarding the calculation of the time constant RC, the predicted value was 6 by multiplying the resistance and the capacitance, and this value was slightly lower, but mostly similar to the calculated value of 6.024. Some possible sources of error in this simulated model would be the neglect of resistance in the ammeter, wire, and the battery, which would not hold true in a real circuit system. While an ideal ammeter has no practical resistance so that all current passes through, a real ammeter would change the current by a small bit, which would impact the circuit that it is a part of. The ammeter would introduce unwanted additional resistance into the circuit system, which would decrease the current by a small amount. If we were to use a real battery to charge a real capacitor without a resistor, our ideal model would predict that the capacitor would charge at a faster rate, as there would be less resistance for the current to flow into the capacitor. This prediction will be slightly faster than the real experiment, as the real battery would have some internal resistance and the real capacitor could have some leakage in the charge, making the ideal calculation different from the real circuit. Thank you for your time and watching this video.